Okay. So the first assignment that's going to be due tomorrow, okay, Thursday, by 9 p.m. Sections P2 and P3, and then P4 on Monday. Actually, let's make that one due. Well, yeah, let's make that one due on Tuesday. 5/18. And the first web assignment that'll also be Tuesday. All right. So make sure you get that turned in by tomorrow, 9 p.m. Scan, complete the assignment on pencil and paper. Scan it using your smartphone with Cam Scanner or Adobe Scan or something similar. Scan it into one PDF file. Make sure the file size isn't too big. You set the resolution down if you have to. And then upload that to Dropbox. Dropbox, again, is right here. So that's the pilot page. It's under the assessment tab right there. Okay. So let's take a look at a few problems in section P3. So if you look on the syllabus, right, for the section, again, we have three types of assignments. We've got the web assigned assignments, the written homework assignments, and just these practice problems. And these are what we'll be discussing at the beginning of class. So for P3, we got 12 to 33 every third problem. Okay, so let's take a look at some of those. And they're all about simplifying these exponential expressions. So how about every third problem? Let's take a look at 21, 24. Oh, how about 24? So practice problems. In section P3, so here's number 24. And there's three parts. So simplify the expression. And in this case, simplify means combine identical factors. And eliminate negative exponents. Not that that's always the right thing to do, but here that's what they're asking you to do. So in number 24a, we've got z squared times z to the fourth over z to the third z to the minus 1. Okay? So that's the expression. By the way, pay attention to the way I'm writing things. And we'll talk more about that as we go along. Now, remember the algebraic identities we talked about yesterday. Okay, where's the one I want to talk about? Number 6 here. A to the n times a to the m is a to the n plus m. You add the factors. Okay, so here with this one, z squared, z squared times z to the 4th, that's z to the 6th. Z to the 3rd times z to the negative 1, that's z squared. And then a to the m over a to the n is a to the m minus n, like that. So this one becomes z to the 4th. And here we have combined all the z's into one exponential expression, and there's no negative exponents, so this would be a final answer. Part B, 2a to the 3rd, a squared. Again, guys, please just turn on your mics and speak. Is there a question? Oh, you're not seeing the screen sharing? Is anyone else not seeing what I'm sharing here?
I can see it.
I can see it fine.
Anybody else not able to see? Thomas, perhaps if you exit the room and come back in, it might work better. All right, with this one, so you can evaluate the inside of the parenthetical expression first, or you can take care of the exponent first. Okay, remember a times b times c to the n was equal to a to the n, b to the n, c to the n. Right? Exponentiation distributes over multiplication and, okay, good. It distributes over multiplication and division. It doesn't distribute over addition, but multiplication and division, yes. So here, maybe we'll do it that way. This becomes 2 to the 4th, a to the 3rd to the 4th, and a squared to the 4th. 2 to the 4th is 16. Now remember, a to the m to the n is a to the m n. M times n. Okay, so this becomes a to the 12th, and that's a to the 8th. And then you have a to the 12th times a to the 8th becomes a to the 20. And now we've combined all the like factors together, all the a's together, and then you got the regular number out front. No negative exponents, so that would be a final answer. C, minus 3z squared to the 3rd, and then 2z to the 3rd. Sorry, my z's look like 2's. All right, let's take care of this exponent over here first. How many factors are there on the inside here? Well, you could think of it as like 3 or as 2. So minus 3z squared, or minus 1, 3, positive 3, and z squared. So I'll do it this way. It's minus 3 squared times z, or sorry, to the third, z squared to the third. And then here we have a 2 and a z to the third. Or you could think of it this way. Minus 1 to the third, 3 to the third, z squared to the third, 2z to the third. All right, so you can distribute the exponentiation over that multiplication in a couple different ways there. Okay, minus 3 to the third or minus 1 to the third times 3 to the third. Either way, you get the same thing. 3 to the third is 27, right? So that's minus 27. This is z to the sixth. 2, and then z to the third. Right, now what else can I do here? Remember, multiplication is commutative. So I can multiply together factors in any order. So using commutativity here, right, it's minus 2.
You have negative 2 instead of negative 27.
Oh, I'm sorry, what happened to my 7? Minus 27 times 2 times z to the 6th times z to the third. By the way, that dot for multiplication is often annoying, so it's better to leave it out if you can, but sometimes it's just confusing without it. A good rule of thumb when writing mathematics is to write things in the most streamlined way possible. I mean, this is what you really mean by simplify. Write things in the most streamlined way possible without any unnecessary symbols. So this silly little thing here is often unnecessary, but if I write 27(2) like that, it looks like 272, so I actually need something there to say it's multiplication. Avoid the unnecessary symbols. They clutter up your expression and make it harder to work with. So that's the essence of simplify. So 27 times 2, 54, so minus 54, z to the 9th. No negative exponents. Identical factors combined. Okay. So that was number 24, right? It's every third problem we're supposed to be doing. I don't need to look at that. I've got one in front of me. Yeah, 15, 21. Yeah, every third problem. So that includes some even ones. So I'll do the even ones, I guess. So 24, so the next even one will be 30. Simplify the following expressions. So, again, there's 3 parts here. X to the minus 2 times y to the 4th. That, oops. To the minus 3 power. So just that. Okay, so let's distribute the exponentiation through. So this becomes x to the minus 2 to the minus 3. Y to the 4th to the minus 3. Multiply. So just because the exponents are negative doesn't change anything. You can still just follow that identity that a to the m to the n is a to the m times n. Okay, so it still works when with some of those exponents being negative. So this becomes x to the 6 times y to the minus 12. Now, in my book, that's fine. That's just fine, like that. That's an acceptable answer. It's written as elegantly as possible, without any unnecessary symbols. But they don't want negative exponents. So what would I do here?
Put y in the denominator.
Yeah, put y in the denominator, right? Like this. y to the negative 12th is 1 over y to the 12th. But then again, you don't want to write it like this either. You want to write it like this. So ideally, you would go from this step to that step without going through this little bit. Okay, but you know, just for now, we'll do it. Alrighty, part B, y squared to the negative 1. Writing here. Y squared to the negative 1, 2x to the minus 3, y to the 4th. All that to the negative 3. Okay. Simplify that expression. By the way, remember, we're only dealing with algebraic expressions here using multiplication and division, and exponentiation, which is essentially multiplication. You know, so we're not mixing in addition yet, or in subtraction. That'll come later. In the next section, I guess. All right. So y2 to the negative 1, that's just y to the minus 2. And then we'll distribute through the minus 3, so this becomes 2 to the minus 3. X to what exponent? So let's skip some steps here. X to which exponent? So it's x to the minus 3 to the minus 3, which just turns out to be
X to the 9.
X to the 9. And then y to the minus 12. Okay, so let's move the negative exponents to a denominator. So this becomes x to the 9th over 2 to the 3rd, y squared, y to the 12th. 2 to the 3rd is 8. And this is y to the 14th. Okay. Any questions? Just stop me along the way. How are we doing so far?
Could you go over 32A?
32A. Yes, we will get to that one. That wasn't one of the assigned problems. I kind of want to stick to the assigned. I'll do it though, but I kind of want to stick to the assigned ones so that we're all working on it.
I think it was a homework one, but
oh, is that one of the ones I assigned for homework?
Yeah.
Yeah. So with that one, follow along with what we're doing here as an instructive example, and then go from that. But we'll start getting into some more involved ones like number 32. So I'll do 33 next, I guess. All right. So I'm sorry.
Would you specifically go over one that has a fraction in the numerator?
Yeah, that's what I'm doing right now. Part C here.
Oh, okay.
Yeah. So this to the minus 3. B to the minus, over 2a squared. All that is squared. All right. So exponentiation distributes over multiplication and division. Right? So we're going to distribute this minus 3 throughout the exponent, throughout this whole thing here, and the minus 2 throughout the expression here. So this becomes 2 to the minus 3, a to the what exponent? Right? I want to skip this step. A to the minus 1 to the minus 3 is just a to the 3. over b to what exponent? Right, b to the minus 2 to the minus 3. Is that cool?
To the 6th.
To the 6th. Everyone, you're so shy, you guys. Talk. It's all anonymous here. Nobody can see you even. B to the minus 2, 2 to the 2, and a to the 4th. Right? So that exponent, okay, I feel like we're not understanding what I'm getting at. Talking and following along is important, guys. Okay, so you wanna do that as best you can. I know sometimes we're kind of shy and we don't want to, but that's part of learning. Okay. All right. So now let's evaluate these. That a to the m to the n is a to the m n again. So, well, the 2 to the minus 3, that's 1/8. This is a to the 3rd. This is b to the 6th. This is b to the minus 2. And this is 4, a to the 4th. Okay. Now, remember, one fraction times another fraction, right? You just multiply the numerators and multiply the denominators. So this is equal to 1/8 a to the 3rd. So one thing I'm also going to do, I'm gonna take this 1/8 and put it out front. So 1/8 a to the 3rd, b to the minus 2, b to the 6th, 4a to the 4th. Right? When I have this fraction in the top of a fraction, essentially I can, right, I mean, if you have like, I don't know, 5/6 x over y like that, you can rewrite this as 5x over y. Put the or 6y. Put the denominator of the fraction up top and the denominator down here. Okay, so that's what I'm getting at here. I want to take this 1/8 and put the 8 down there. And then I've combined these. All right, remember the negative exponents, if you've got ax to the minus n over b like this, take that x to the minus n and you can put it down here and make it a positive exponent. Or the other way around, you have the minus x to the minus n here, you can bring that up top and make it a positive exponent. See that? If you have a fraction and a factor with a negative exponent up top, you can bring that down below and make that exponent positive. Or if it's down below, you can bring it up top. So we're going to apply this here with this b to the negative 2. So that's a to the 3rd. And then 8 times 4 is 32. B to the 6th, b to the minus 2, a to the 4th. Okay.
Do you mean b to the positive 2 in the denominator?
Oh, b to the positive 2, I'm sorry. All right, now this becomes b to the 8th. 32, b to the 8th, and then a to the 4th. Now, how are we going to take care of this a to the 3rd over a to the 4th? Remember, a to the m over a to the n is equal to a to the m minus n. Another way to think about doing this is to think about like canceling factors, right? So if you have a to the m over a to the n, and maybe there's another factor in the fraction b like this, one thing you can do is you can sort of cancel some of the a to the m's. Right, so this becomes a to the m minus n over b. So you subtract the factors of a from the on the bottom from the top. So that's a way of combining them. It's another way of using that a to the m over a to the n is a to the m minus n. So it's another way of using that when you've got more factors on the bottom or on the top of that fraction. Something like this. So here we want to cancel these. So because there's more factors on the bottom, you want to cancel from the top. So 3 a's from the bottom leaves 1a, or so 3 a's on the top from the bottom leaves 1a on the bottom. So since we've canceled all the factors on the top, that's left with a 1, 32 b to the 8th. Right? So maybe perhaps that's the way you've interpreted the factors on the top and factors on the bottom thing using this cancellation method. But that's the final answer right there. All right, so let's do some more with these fractions. So something like 32. 31 is a nice one. 33. Let's check out 33, I think. 33 is not a great one. 31 is nice. Let's try 31. So this is not one of the assigned ones, but it's a good practice for 32. So A is 3x to the minus 2 y to the 5th over 9x to the minus 3 y squared. Okay. Move the negative exponents from top to bottom to make them positive exponents. So 3x to the 3rd y to the 5th over 9x squared y squared. Now let's do these cancellations. There's 2 factors of x on the bottom, 3 on the top. Okay, so we're going to cancel the 2 on the bottom with the 3 on the top, leaving 1. Cancel the 2 y's on the bottom with the y's on the top, leaving 3. 5 minus 2 is 3. All right, that's 5 factors of y. That's 2 factors of y. Cancel the 2 factors of y on the bottom with the 5 on the top, leaving 3. And then the 3 and the 9 cancel, leaving a 3 on the bottom. Right? Same idea. This is 3. This is 3 squared. So there's 1 factor of 3 on the top, 2 on the bottom. So what we're left with on the top is just y to the 3rd over 3, xy to the 3rd, sorry. X to the 1, y to the 3rd, over, and everything on the bottom is gone except that 3. All right. So no negative exponents like factors combined. So that's an acceptable answer. I would also like this, count that as an acceptable answer as well. You know, there's always a little bit of sort of subjectivity in what you mean by simplify. You know, just write it in the clearest way possible is what it means. B, 31. 2x to the 3rd, y to the negative 1, y squared. And that whole schmear to the minus 2. So let's distribute the exponent. 2 to the minus 2, x to the 3 to the minus 2, y to the minus 1 to the minus 2, y squared to the minus 2. 2 to the minus 2 is a quarter. X to the minus 3 to the minus 2 is x to the minus 6. And then this becomes y squared. And this is y to the minus 4. move negative exponents from top to bottom or bottom to top to make them positive. The 1/4 on the top, leave the 1 on the top and put
Are you able to slow down a little bit?
I'm sorry?
Are you able to slow down a little bit?
Sure. So the 1/4, again, guys, if you're taking notes, I would encourage you not to take notes. Okay, I've got these notes posted online for you. So what you want to do is download those. And the other thing you want to do is the following. So you see that I'm doing these problems and writing out the solutions for you. You're going to want to redo these problems on your own and check your work against mine. Make sure that you're getting the same or similar answers. Okay? So with the 1/4, leave the 1 on the top and put the 4 on the bottom. With the y to the negative 4 on the bottom, bring that to the top and it becomes y to the 4th. And with the x to the minus 6 on the bottom, top, bring that to the bottom, make it x to the 6th. And then y squared up here. So this becomes y to the 6th over 4x to the 6th. All right, part C. Y to the minus 1, x to the minus 2. To the negative 1 power. 3x to the minus 3 over y squared to the minus 2 power. Distribute through the exponent. So y to the minus 1 to the minus 1 is just y. X to the minus 2 to the minus 1 is x squared. 3 to the minus 2. X to the minus 3 to the minus 2 is x to the 6th. Again, multiplying the exponents, multiplying the exponents. And then y to the 2 to the minus 2 is y to the minus 4. Combine the two fractions together. So, right here we got these variables x and y, right, or these unknown quantities x and y, and then you have the 3. The 3 is a known quantity. So what's customary is to put that one first, is to put the actual number as the first factor and all the unknowns after the actual number. So 3 to the minus 2, right, that's 1/9. Y times x to the 6 over x squared y to the minus 4. Let's take the y to the minus 4, bring it up top. As y to the positive 4, x to the 6th over x squared. 2 factors of x on the bottom, 6 factors of x on the top. Taking away leaves 4 factors of x on the top. Right? Y, what's this y times y to the 4th? How do we evaluate that?
Y to the fifth.
Y to the fifth. Remember, there's always an exponent of 1. Right? And then here, same base, different exponents, just add the exponents. So y times y to the fourth, that is y to the fifth, x to the fourth. And then on the bottom, we've canceled all the factors out, so that's just a 1. So instead of just putting it over a 1, you could just, leave it out and just leave this as, so again, I kind of like this as an answer. But another way you could write the answer would be y to the fifth, x to the fourth over 9. I think this is more what the book wants you to write. Although I kind of like it like this. I mean, it uses some extra symbols, but again, it's customary to put the number in front. And 1/9 is a number. Right, so it's treated somehow a little bit differently than the unknown quantities. So either answer to me is fine.
I have a question.
Mm-hmm.
So does it matter where you put like the letters? So like, could you put x to the fourth, y to the fifth over 9, or does it have to be y to the?
No,
What's up?
either order. Actually, probably if you put x first and then y, I mean, it might be a little nicer because
Okay.
it's in alphabetical order. Not that it really matters, but
Yeah.
multiplication is commutative, so you can present the factors in whatever order that you like. The only sort of caveat to that is that normally you put the number out front if there is an actual factor that is a number. In this case, the 1/9, or if it was just
Okay.
a 6 or something.
All right. Thank you.
Okay, so so for number 32, okay, let me start that one off for you. So this is one, of course, that you need to hand in. But let's start it off. Here is a start. So we've got 1/2 a to the minus 3 b to the minus 4 over 2a to the minus 5 b to the minus 1. Okay. Again, you've got this fraction on the top. Right? Whenever you have a fraction like this, so you have this kind of situation. You have a fraction on the top, p over q, within a fraction itself. No addition here, just multiplication. Multiplication and division, of course. This can be rewritten by putting, I mean, there's a couple steps you can go through to get to where you want to be. This can go out front as another fraction. Like that. And then this just evaluates like this. But really, it's nice to go from here to here right away. So I've got this fraction on the top of another fraction itself. Leave the numerator in the numerator, the denominator in the denominator. Okay, in a fraction that's only using multiplication. Multiplication and division. So here we've got this 1/2 there. So the first thing I want to do is put the 2 on the bottom. So a to the minus 3, b to the minus 4, 2 times 2, a to the minus 5, b to the minus 1. And then shift those negative exponents top to bottom. Right, so the a to the minus 5 on the bottom of this goes to the top. A to the minus 3 on the top goes to the bottom. B to the minus 1 on the bottom goes to the top and just becomes B to the 1. B to the minus 4 comes down here, and then that's a 4. I committed a... Okay, there's more to do. We got to combine the A's and the B's. Okay, we need to combine the A's and the B's. Basically, we're going to do some canceling. We're going to cancel the 3 A's on the bottom with the 5 A's on the top, leaving 2 A's on the top. We're going to cancel the B on the top with the 4 B's on the bottom, leaving 3 B's on the bottom. All right, and that'll be the end of that. Okay, so, give 31 a go on your own. Right, 31's a nice problem. Give that one a go on your own and compare your answers against mine. Right, and then if you're able to do that, then 32 won't be a problem. Okay.
Thank you for going over that.
No problem. Alrighty, so we're done with section P3. There's one final topic in P3. I'm not going to ask you any questions about it, but we do need to go over it a little bit, and that's called scientific notation. Right. Consider the exponential expressions of 10. Or the powers of 10. Right. 10 to the 0, of course, is just 1. 10 to the 1 is 10. Shift that down a little bit. 10 squared is 100, 2 zeros. 10 to the third is 1,000, 3 zeros. 10 to the fourth is 10,000, right? A 1 with 4 zeros, and so on and so forth. 100,000. And then we've got the negative exponents of 10 as well. So 10 to the minus 1, well, it's 1/10, right? But as a decimal expression, it's 0.1, or just 0.1. 10 to the minus 2 is 0.01, 1/100. 10 to the minus 3 is 0.0001, or sorry, 001. 10 to the minus 4th is 0.0001. So there's a little bit of a, difference between the positive and the negative exponents, right? Like 10 to the 4th is a 1 with 4 zeros. Right? 10 to the minus 4th is 3 zeros, then a 1. So the number of zeros here differs from the exponent, whereas the number of zeros here is the same as the exponent. Okay, so using these powers of 10, expressing very large numbers or expressing very small numbers is often easier when you state them in terms of powers of 10. Right? So when we write, so these are useful. For expressing very large or very small numbers more clearly. Not clearly, but succinctly. more succinctly and clearly. All right, if I want to say, like, for example, if I want to say like 7.85 trillion, right? 1 trillion is 10, or not trillion, that's too big. 7.85 million. And when somebody says 7.85 million, means 7.85 in a million is 10 to the 6. It's a 1 with 6 zeros. Right? 1, 1, 2, 3, 4, 5, 6. That's 1 million. So when we want to say 7.85 million, that means 7.85 times 10 to the 6, which is an easier way of writing of writing 7,850,000. Notice the difference in where the decimal place is between the two expressions. 7.85 and 7.850,000. The decimal place is here, which is 1, 2, 3, 4, 5, 6. 6 spots. Sure, yeah, in chemistry, high school chemistry may be the first time you saw that. Right, but then again, when you read the news these days, people are always talking about, big numbers, and they'll often say it, 7.85 million, 1.2 billion. Right? What does that mean exactly? Well, this is what it means. Okay, so when you say 7.85 million, what you want to do is write 7.85 times 10 to the 6. And the 10 to the 6 means shift the decimal place backward 6 spots. Right, so you have 7.85, and you shift the decimal place back 6 spots, and then that gives you 7,850,000. Sometimes these numbers with all these zeros, you get caught up in counting how many zeros there are. Here it's telling you, okay, shift the decimal place back 6 places. Well, I mean, because this has got a decimal expression there, it doesn't mean 6 zeros, but it means shift back 6 places. But you don't have to count how many number spots there are anymore when you write it this way. Another example. $3.5 billion is 3.5, and a billion is 10 to the 9th. So you take 3.5, and we're going to move the decimal place over 1, 2, 3, 4, 5, 6, 7, 8, 9. So we've got the 5, and then we fill it in with zeros. And then here's the decimal spot. So in the end, what do we have? We have 3, 5, 0, 0, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And then, block them into chunks of 3, starting from the back. right? And that's 3.5 billion. But looking at this, it's kind of like, well, what's that number? What is that? I mean, let me count the zeros, right? It's easier to say 3.5 billion or 3.5 times 10 to the 9. And then you can also go the other way. 3.5 times 10 to the minus 7 means shift the decimal place to the left 7 spots. So here we've got 3.5. Now I'm going to shift the decimal place 1, 2, 3, 4, 5, 6, 7. And the new decimal spot will be here. So what we're left with is this. So that's 0.00, make it in black, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8. All right, so 0.00000035, that's 3.5 times 10 to the minus 7. And on your calculators, you have that functionality built in. So, for example, if you use a Windows computer, there's several calculators that come with it. Here's one right here. See, I've got that button on the calculator right here. So, for example, if I want to write 8.5 times 10 to the 6, so unfortunately it uses this weird notation, 8.5e plus 6. That means 8.5 times 10 to the 6, right? 8.5 times 10 to the 6. And then if I hit the equal, it'll if it's not too big, it'll write it out for me with all the zeros that it needs. So that's 8,500,000. But it won't go too far, right? If I wanted to do 1.235 times 10 to the 9th, let's see if I'll go to a billion. Yeah, so 1,235,000. I don't know how far it goes. 1.2 times 10 to the 12th, that's a trillion. Oh, it does that too. Right, so instead of entering a number with all these zeros where you might make some kind of error in how many zeros you stick in there, you can always use this kind of functionality on the calculator. And then when it gives you an answer in terms of these exponential expressions, you can translate it back to an expression using just the zeros if you want. Okay, so that's just something to keep in mind when you read the news. People are often talking about big numbers. So they mean, oh, this sales from this company this year were 2.5 billion. Well, what does that mean exactly? 2.5 billion. Well, it's 2.5 times 10 to the 9th. Right? Or the budget deficit this year is 1.2 trillion. So that's 1.2 times 10 to the, 1.2 times 10 to the 9th. The billion is 10 to the 9th. Well, that's what it means. Okay? Or, a hair, the hair on your, head, the thinnest ones are, I don't know, 3/1000ths of an inch across, 3/1000ths of an inch across. What does that mean? Well, that's 3/1000ths. A thousand is 10 to the 3rd. So here we're talking about 10 to the minus 3. So that's 0.003. Okay. So no problems on that. Just something to keep in mind when you're working with numbers. All right. What time is it? 10:46. Moving on to section P4. I have notes for it somewhere. Let's see. There it is. So section P4 is on rational exponents. What's a rational number? What's a rational number?
Isn't it like all real numbers?
Actually, no. Actually, no. A rational number is a fraction, well, is a whole number, well, an integer, let's say, or a fraction of two integers. A over B. So, for example, right, minus 3/5 is rational, as is 5/3 is rational, as is 216 over 2 something. Well, that's actually an integer. That's an integer as well, over 5. You know, I mean, whatever. A fraction of two integers, that's a rational number. Not all numbers are rational. Actually, in some sense, most real numbers are not rational. That's a little bit more advanced than we want to get into, but examples of this are like square root of 2. Square root of 2 is not a fraction of two integers. That's probably the easiest number to explain why it's not rational. To explain that the square root of 2 is not rational is probably the easiest one, although it's not easy. And then there's like pi. Explaining that pi is not rational is actually pretty involved. And then there's that Euler's number, E 2.72. All rational numbers have, sorry, all irrational numbers have these infinite decimal expansions that don't have a repeating pattern of any sort. Right? I mean, of course, 1/3 has got a decimal expansion, but it's a repeating one, or and there's plenty of them, of course, right? A finite decimal expansion is also always 2.25 is also always rational. So repeating expressions and finite decimal expressions, those are all rational numbers. But if you've got an infinite decimal expansion that doesn't have a repeating pattern, that's an irrational number. But that's a pretty advanced topic. We're not getting into that, but just so we know, so we've heard it before. All right. So exponents with rational exponents, instead of just using integers, oftentimes you can encounter rational numbers as exponents, and then you can have any real number as an exponent as well. But we start with the rational ones. Okay. What does this mean? Square root A equals B means what? b is the real number such that what? What does b do? If you say b is the square root of a, what does that mean in terms of what we've already been talking about? Right, we've been talking about integer exponents. So in terms of integer exponents, what does square root of a equal to b mean? It means that a is equal to
B squared.
b squared, right, which is b times b. All right, we've already talked, we know what b times b is. Right, we've already talked about that. B times b, that's b squared. Right, so now we define the square root of a in terms of what we've already been talking about. Right, it's not something that it's not something that just sort of exists on its own. It's a consequence of ideas we've already been discussing. So square root of a equal to b means that b is the real number such that a is equal to b squared. So for example, the square root of 9 is what?
3.
3. The square root of 3 squared is, so what number, sorry, b is the positive real number. I said that wrong. B is the positive real number such that a is equal to b squared. Well, here, 3 squared, again, that's 9, and the square root of 9 is 3. But what about this?
It's the same thing.
It's still 3. Negative 3 squared is negative 3 times negative 3 is 9. So that's still 3. It's not negative 3. The square root is always positive. So more generally, the square root of x squared is not necessarily x. Right? If x is equal to negative 3, the square root of negative 3 squared is not negative 3. It's 3. The square root of 3 squared is 3. Square root of negative 3 squared is 3. So in general, the square root of x squared is what? What expression do we use to make something positive?
We invert it.
Yeah, well, there's a symbol that we use, and we actually have a name for that, right? Absolute value. Yes, your intuition is right. It's absolute value of x. Okay, so square root of x squared is not x. Well, not necessarily. Not necessarily x itself. For example, when x is negative, the square root of x squared is not x, because x was negative, and square roots are always positive. Anyway, other numbers that that have nice, neat answers. The square root of 4 over 25. What's that going to be? Actually, we got to go. It's 1056. Well, that's 2/5. Right? Remember, a fraction times a fraction. You multiply the numerators and multiply the denominators. Okay. So that's all for today. Okay, let's get that assignment number 1 done and submitted. We'll talk a little bit about it tomorrow if we get time. Okay. Have a good day, everybody. Email me with questions or concerns. If you need a little help, okay, email me with questions, or if you want to meet, we can get a time to meet for a little while, all right? Okay. All right, guys. Have a good day.